Hi, I'm Yue Ren. I'm currently a master's student at University College London, the Butler School of Architecture. My research topic is about machine learning and its application in architectural design. I'm glad to be here to present our paper, The Spell of AI, Voxel-based 3D style transfer, in cooperation with Hao Zheng from University of Pennsylvania. The introduction. Machine learning, a decision-making tool, takes inputted factor as training neurons and calculate the computational relations among the input and output data. Thus, deep learning as a popular machine learning method contains a class of trainable neural network with multiple layers. That low-level feature in the first layer are combined into high-level features for precise classification in the last layers. Convolutional neural network, a representative algorithm for deep learning, is widely applied for visual imaginary recognition analysis. The core working structure of CNN can be summarized as differentiating scoring simulator with 5 layers: input, convolutional, pooling, ReLU, and loss layer. According to CNN BGG19 model, feature signals are continuously superimposed and passed on to high-dimension classified layers. And based on the workflow of CNN, neural style transfer refers to a representation system according to Justin Jason's code that manipulates digital image to combine the visual style of another image. It was first introduced in the neural algorithm of artistic style by Leon A. Gattis, with the core innovation of a pre-trained deep learning network. With the pre-trained process, the machine focuses on learning different features of a content and the style in each layer of VGG19 model. During the operation process, users only need to input a content image and the style image with the pre-trained framework. The editing process behind contains a series of optimization through gradient descent of content and style loss. According to the formulas, content weight alpha and style weight beta are the main influence parameters for generating image G. When the content weights keep constant, the addition of style weight would result in a higher similarity between the style and the generated image. Thus, the total amount of the style weight and the content weight in all layers is 100%. Different proportions division of alpha and beta in each layer will also result in a different output resolutions. Neural style transfer is initially applied in the art field, for example, the stroke mapping. There are a few breakthroughs recently in architectural fields for introducing 3D modeling concepts. For example, single feature of a source model can be extracted and added to a target model for a new output. Another approach is to use a transfer algorithm for mapping images to the model surface to change the patterns, which still work with plane surface without changing the geometries. Object can also be provided with multi-angle rendering system that the stylized image are mapped back into a 3D model. The network fits style on 3D object, but also has limitations with fixed perspective and solid model with few geometric possibilities. So, is it possible to develop style transfer as a 3D form-finding tool in architecture design, rather than just an art renderer for pixelized image? Our proposed method can be summarized into two mutual steps: the transformation and recreation between the 3D voxelization volume and 2D pixelized images. For the detail of the process, users firstly get their demanded closed 3D geometry. The model is then cut into multiple plans to match with the 2D style transfer data structure. Meanwhile, user can fill the interior boundary surface as black, while the exterior surface as white, and export all the color plans as single images with certain resolution. And the interior area is defined as the content for later training. Larger RGB difference between the adjacent of the style image result in a higher distinction of the machine learning data. With the edited 2D content images and the 2D style image, user can then input them into VGG19 network for adjusting the key parameters. There are 4 main style training parameters: the total amount of the content weight alpha, the total amount of the style weight beta, the proportions of the content weight in each convolutional layer, the proportions of the style weight in each convolutional layer. The first two parameters work to control the general fitting tendency, and the last two proportions control the learning details. In the final step, the set parameters are correspondingly assigned to the style image and each content plan. Then the style transfer training starts. Before having further addition, there are two main settings for output standardization. First, the interior area of the standardized result should be abstracted according to the content boundaries. Thus, the pixel RGB value of the image can be unified into corresponding grid values, which can be represented as a readable grayscale file. These pixel points are also placed back into the original 3D location for building the original volume. Moreover, three feature factors of the spatial points are defined for controlling the final output: the grayscale filtration value of the pixel points, the number of the closest pixel points, the distance domain of the closest pixel points. After getting all the spatial pixels, user can adjust the filtration degree by setting a certain value within the grayscale domain. These pixel values that are smaller than the setting are remained, others that are larger are abandoned, and finally all the abstracted points are obtained. To convert the 3D lattice into a form geometry, the basic elements of the voxel modeling is then placed to filtered points for generating the voxelization structure. The adjustment of the grayscale value is then visualized as a Holding density that controls the contribution of the solid and the void area. The original style image also becomes the interior structure basis rather than a plain pattern on the surface. For enriching the expression of the geometry, the smoothing algorithm is applied for the final form modification apart from the style transfer network. With the increase in the number of smoothing iterations, the angularity tends to be much more sleeker. Users can also choose the visual types such as Gaussian and medium according to different visualization needs. So what result can we generate for a certain design problem? In order to add more reconstruction meaning to the real-world form-finding process, the Spire of Northern Dim Cathedral is chosen for rebuilding the next step to test the performance of the methodology, which also explores the possibility of AI manipulation within the historic culture context. First, in the data preparation stage, it is necessary to edit a closed mesh and a simplified model of the spine as a content model with specific file requirements. Second, the re-edited model is then cut into a series of plans for matching the spine content with the 2D training structure of the style transfer. The cutting level and the plan number need to be based on each building's length, weight, height ratio. Thus, according to the actual measurement of the spine and the scale collection in the random model, the spine is decided to be divided into z-axis direction with the distance of 1 unit. As a result, 406 clone contours are generated. Then, by defining the spine interior as a content and distinguish the interior area as black box, 406 content images are exported in the top viewport with resolution of 50 × 50 pixels. For the style image, the Gothic ornamentation of the rose window from the Northern Dim Cathedral is selected for connecting with the architecture. The color of the line and the background are all removed, and the overall contrast is raised for better visual effects in later training. With the content plan and a modified style image, content weight, style weight, and their representative proportions in the 5-layer of VGG19 are considered in the next step. However, since there is a certain unpredictability of a style output, another experiment process is decided to test the possibility influence of these feature parameters. To be specific, 3 plans extracted from the bottom, layer 000, medium, layer 170, and the top part, layer 340 of the spine is chosen for the testing. The variable adjustment focuses more on the style weight, testing from 0 to 2000, and the final optimized ratio between the content weight alpha and the style weight beta is decided to be 300 to 125 to 300 and 1250. Thus, in order to increase the visual diversity for later training effects, the style weight is decided to be gradient change instead of single linear increase. In accordance with the volume recreation methodology, previous output are then converted into a standardization grayscale file. Final effects of the spine are presumed through 3 geometry settings: the grayscale cutting rate, closest point number, and the closest point distance. The 3 sets of data are all said to be in a balance effect between the segmented and continuous effect with rich details. The smoothing algorithm is then used with multiple values to replace with voxelization box with spherical surfaces. The additional Gaussian smoothing type and the number of the smoothing iteration domain are all adjustable to transform the outcome into customized geometries with multiple design options. In conclusion, machine learning style transfer is an ideal tool for architectural form finding. By inputting various content value, customized data, and feature parameters, designer can generate diverse 3D forms with customized styles. This voxel-based method also has a great potential in the future for inspiring CN structure as a possible development of 3D voxelization style transfer. And that's all. Thank you for listening.